This is Hacker Public Radio episode 3319 for Thursday, the 22nd of April 2021. Today's show is entitled Linux Inlaws S01E28, Politicians and Artificial Intelligence Part 1. It is hosted by Monochromic and is about 67 minutes long and carries an explicit flag. The summary is part 1 of a miniseries on IML, DL and other fun.
This episode of HPR is brought to you by anhonesthost.com. Get 15% discount on all shared hosting with the offer code HPR15. That's HPR15. Better web hosting that's honest and fair at anhonesthost.com.
This is Linux Inlaws, a podcast on topics around free and open source software, any associated contraband, communism, the revolution in general, and whatever else fancies your tickle. Please note that this and other episodes may contain strong language, offensive humor, and other certainly not politically correct language. You have been warned. Our parents insisted on this disclaimer. Happy Mum? Thus, the content is not suitable for consumption in the workplace, especially when played back on a speaker in an open plan office or similar environments. Any minors under the age of 35, or any pets, including fluffy little killer bunnies, your trusted guide dog, unless on speed, and cute T-Rexes or other associated dinosaurs. Good evening, Martin. How are things?
Good evening, Chris. Things are fine and dandy, as they would say, across
Excellent.
the pond.
How's the
How are
lockdown?
you? How are you?
Not too bad. How's the lockdown treating you these days?
Same as before.
Hmm.
It hasn't changed as such.
I see. Very good. Very good.
Mind you, did you mention hairdressers opening last time? No.
I think I did.
They haven't opened here yet, but they are soon.
But then you get vaccinated left, right, and center, apparently.
Well, we are ahead of most countries. Which makes a change.
Some people would call that stealing from Europe, yes, but we won't go down that route. Anyway,
well, no, the
doesn't
Europeans
matter.
are just being very silly about it.
Indeed.
Anyway, let's not go there.
Yes. Okay. No.
We are not a political show, after all.
No. This is not the Brexit podcast for some special reason.
Russian communism excluded.
But rather, the Linux Inlaws now will talk about. What will we talk about tonight?
Well, you can talk about. People use a lot of terms for these things like artificial intelligence, data science, machine learning, deep learning, lots of kind of terms being thrown around. But hopefully she'll clarify some of these today.
Indeed. So in the olden days, that would be known as Margaret Thatcher.
What?
Sorry, let me repeat that.
What?
So in the olden days, these concepts would be all rolled up into one called Margaret Thatcher.
Because
the first project that terribly went wrong.
Okay.
That went wrong terribly. Sorry, we probably have to cut this out because it's a political joke.
Yeah, and it's slightly confusing.
As most of my jokes are.
I don't get it. You may need to. I mean, Thatcher was a politician in the 80s, right, or whatever it was. But
yes, correct. But you see,
I didn't know she did anything with machine learning back then.
No, but she was an artificial intelligence. No,
was she? Oh, she was one. Right.
We're getting there. Wow. We're getting there.
Okay.
Sorry.
Well,
going back to somewhat safer ground now.
It's a bit of a far-fetched link. I'm sorry.
I do apologize.
I'm not in the equal amount of beer at the moment, obviously.
Okay. Fair enough. This is my second bottle. I mean, this is nothing. This is just warming up.
Okay.
And I'm running low on this stuff, actually. Okay. Before we go into the details, yes, let's cover some of the basics first. There is, of course, the wide and open field called machine learning.
No. What about artificial intelligence?
Sorry. Anything not human.
What about plants?
Does that qualify?
Do plants not have intelligence and cats and dogs and stuff?
Sorry, anything not living and breathing?
Okay.
Makes sense? Yes, no, maybe?
It's quite reasonable, yeah.
Full disclosure, for the wet, where beings listening to this podcast, you may get offended further down the road, but don't worry about it.
For the what, sorry?
For the wet, where beings listening to this podcast, as in the gray zone between artificial and real intelligence.
Oh, I thought you were talking about fish. Okay.
No, you know something called the Terminator?
Well, there was
like a computer inside a human, or the other way around. There is a gray zone.
That would be a bit of a design flaw, wouldn't it?
Man, the fact that I'm alluding to that there is actually a gray zone, so it's not as black as white as some people would make you believe.
I see. Very good.
Okay. Artificial intelligence, not necessarily walking, running, breathing, and other stuff.
Well, learning, solving problems, making decisions, stuff like that. No.
Yeah, but that would qualify
as intelligence, no.
Yeah, but that would qualify. But that may be artificial intelligence too, no?
Well, this is why I'm asking. So,
sorry. Okay, intelligent beings. Anything outside politics. Make sense?
Well,
okay.
And the state agents,
yes,
lawyers, managers.
Okay.
Sorry.
Okay, artificial intelligence. Anything outside the gray zone and biological beings, I suppose.
Okay. Yeah, go for it.
As an originally man-made. I think that's the most fitting definition, I suppose.
Well, that includes the aliens, I guess. But yeah, that
sorry, man-made as in. Sorry, yes, aliens. If you're listening, please send email to feedback@linuxinlaws.eu.
We are trying, language we can understand.
Yes, we are trying to be a politically correct podcast, but sometimes it doesn't work out.
Indeed. Right.
Okay.
Coming
back to machine learning. Why is machine learning so important, Martin? And I don't want to hear the word politics these now.
Why is it important? Well, it depends who you ask, right? If you ask... I'm
asking you.
Okay, if you're asking me, then for me it is a fact that you can automate mundane tasks that would require some human-like qualities, like being able to recognize speech, images, those kind of things, and making decisions based on those. And you want to do that for the tasks that people don't want to do, really.
So would it be fair to say, or to assume rather, that machine learning would entail some sort of computer in one shape or another?
That would be fair.
Sorry,
yes.
Algorithm, not computer, but algorithm. Let's put it this way.
Yeah, no, that's fair. Definitely algorithm is good. Yeah, it doesn't have to be. Well, I mean, it depends how you define computer, right? If it's people think of computers as things with electronics and stuff, but a calculus is also a computer, right? Because you can compute things on it.
True.
Anyway, so
yes.
Yeah.
True. A computer in the widest meaning, in terms of a Turing machine. Deterministic or not.
Indeed.
Links, of course, will be in the show notes. Alan, if you're listening, no sweat, we'll provide definitions. Sorry.
Actually, yeah, we should get him on the show.
You don't know who's listening to this, right? I
That's very true. Very
this
true.
is not
He might want to come on the show.
Confined to the living beings. No, yes.
Indeed.
Do you know a medium?
Well, there's
that we could ask.
there's a popular writing website called Medium.
Exactly. That's not what I'm talking about, Martin. No, it's not medium.com.
No,
anyway, okay.
Yes, going back to where we were. Right.
Exactly. Okay.
Yeah, what is your opinion on this then?
Machine learning has been around for ages, right? I mean...
No, but why would you...
What do you mean?
Well, why would you want to use machine learning?
Because humans are stupid, right? As we all know. We just have to take a look at politicians, best example.
Well, because humans are complex, I think. This is
most of them would be stupid, especially
humans,
politicians.
Human, if you're listening.
Sorry, let me rephrase that. Actually, machine learning, of course, would be the next step towards a better being in terms of the next step of the evolution.
Okay.
No, yes, maybe. This is a very controversial statement. I know this.
It is a controversial statement, and also the technology isn't quite there, is it really? But yeah.
But in comparison to the 50s, we have advanced a little bit, I suppose.
We have, yes, we can do.
Because the 50s
things.
was actually the first point in time, I would reckon, where mankind thought about putting computers to good use in terms of artificial intelligence as an intelligence in computers.
So how do you define good use?
Coming up with the concept and thinking about the consequences, to some extent.
No. But I mean, you know, what is a good use of a computer? Right? Is it
advancing mankind?
Okay, it's not many are used for that, I would imagine. But, yeah.
Okay, Mr. Schwarzenegger, if you're listening, this show is for you.
Oh, we could get him on the show as well. He's not dead, at least. Makes it slightly easier.
True.
Okay. Where were we? Right.
History, as a matter of fact.
Oh, yes. Okay. History. Yes. So
the thing is basically this whole artificial intelligence and machine learning was kind of, well, the basics were all the rage in the 50s and 60s, but then it somewhat died down because the technology wasn't quite there.
Indeed.
Because mostly you were talking about mainframes, and the mainframes had limited computing power, never mind storage and bandwidth and all the rest of it. So I think in the oversimplifying things in the 70s, 80s, and 90s, I wouldn't say that artificial intelligence took a hibernation of sorts, but I think that's not too far from the truth.
Yeah, it's very fair to say the computing power wasn't there, right? So
yes,
very true.
And then came, of course, a startup called Google. with the disposable income at hand to change things once again. For the last, I reckon, 10 or 15 years, something especially called especially machine learning in the shape of deep learning has been all the rage, right?
Well, it depends what you call rage, but it is. Google's probably the best. Well, there's Google, Facebook, Amazon. They're all using it, right, and developing it.
So Martin, what's the difference between machine learning, as in machines that are learning, and deep learning?
Well, deep learning the difference is that deep learning uses self-training neural networks, whereas machine learning is really an algorithm as such that someone has developed. If you think about solving the problem, you can boot out with a whole bunch of if statements, right? But it would be many if statements. So you'd be there for a long time. So why not use a computer to do that for you instead?
Before we go any further, we should probably explain what a neural network is.
Okay, we can do that. Yes.
Yes. The beauty about a neural network is actually that everybody has one, at least, if not more than one.
Well, you say that.
Maybe apart from politicians, but
I'm not entirely sure if we have the same functionality in our brains, but it's loosely based on that, right?
Okay. At the end of the day, it's okay. What defines a neural network? Basically, it's interconnected cells that are capable of modifying their behavior. Let's put it this way. This definition, don't quote me, is very loose, of course. Behavior in terms of the way they process signals.
Mm-hmm.
If you take a look at the human brain is made up of. I'm grossly oversimplifying things now, but not everybody is a neurobiologist. Listen to this podcast, so I just might get away.
You're right.
So at the end of the day, basically, you have neurons.
So what is a neuron?
Exactly. It's
what do you mean
cell.
exactly?
Sorry. A neuron, if I could just finish, a neuron is a cell that is capable of transmitting electric current. And the second characteristic or trait of a neuron is actually that it can change the way it transmits this current. It transmits that current.
Okay. How does it do that?
Chemical foundations, as a matter of fact.
Okay.
We won't go into the details because that episode is only about 3 hours long. If we would go into the details, we would be easily looking at 6 hours. No, in a nutshell, basically, neurons are able to change the way they transmit that current.
Okay. So I guess one question here is, are they able to change this current in an analog way?
Neurons only work on an analog basis.
Okay.
They modulate the current in contrast to computers, which normally are actually operating in a binary fashion.
Mm-hmm.
Unless you're talking quantum computers and all the rest of it, but more on that in a later episode.
Yeah, maybe in 5 years' time when they're actually accessible to mere mortals.
Yes. D-Wave, if you're listening, the email address is sponsor@linuxinlaws.eu.
Send one over now.
Yes. In case you're wondering what to do with all that money.
Indeed.
D-Wave, of course, being one of the first companies offering quantum annealing computers on a commercial basis. Same goes for a company called IBM or Watson, if you're listening.
Well, if it's Watson, he probably is, indeed, yes.
The email address. Anyway, I digress. Okay. Back to the basics. Okay. The idea with artificial neural networks is pretty much the same. You have a simulation of a neuron that takes input values comparable to that input that current flowing into a neuron, and then does something with it. Normally, this is where the magic is. This is where the magic source is, as in the function that takes the input value, and then basically comes up with an output value. And in traditional artificial neural networks, this function would have one important property called something called a weight.
So it's basically a function.
Exactly. And a very primitive neural network basically would just essentially take the input value, apply the function to it, factor in the weight, and then produce an output value. Now, the beauty is basically you modify this weight, you get a different behavior of the function. And this is how something called backpropagation networks work. In terms of sorry, Martin, go ahead.
Yeah, before you move on to backpropagation. So if we, because we don't just have one neuron, right? We have a bunch of neurons.
Sorry, yes, Martin. Correct, of course.
Interconnected, yes. In layers, right? And there's two main layers, the input layer and the output layer, and then a whole bunch in between, depending on what you want to do with it.
In traditional artificial neural networks, yes, correct.
Yeah, well, I mean, you have to have an output layer because you have to have something that says whether it's a cat or a dog, right? So,
Martin is skipping ahead, but that's okay.
Anyway, no, but it's just describing the whole network, right? So you have a bunch of neurons that are decide the input. Yes. Well, your input layer, and then you got a bunch of stuff in the middle where connections happen, and then there is your output layer that just makes the final decisions on what you want it to do.
For the following discussion, it may help to define a Markov chain. Before we progress to hidden Markov chains, sorry, that was a joke. We won't go there. This is not a this is not a podcast on maths, but rather we'd like to keep it simple.
Well,
for the people,
having said that, it is all related to maths anyway, or based on maths. No, but yeah. So,
yes. Okay. Now, as Martin rightly interjected, normally neural networks consist of several layers, and the idea behind these layers is coming to something called now backpropagation networks. There's one phase basically called the training phase, and then there's the what's called inference phase. Exactly.
Inference,
yes.
Yeah.
Inference. Yes. Sorry. And the idea is basically during the training phase, you actually modify these functions, including the weights.
Now, when you say you mean not you, really, do you? But,
No, I must have personally. I don't know about you.
Because that would be quite a busy task doing that for a network with many neurons. Right?
Okay, Mark, why don't you explain backpropagation networks, BPNs, in a little bit more detail?
Okay, so we have our layers of neurons, right? So if you imagine your input layer neurons, every neuron on your input layer neuron is connected to the next layer, to neurons in that layer, right? So if you imagine think of your nodes in a network, all your nodes on your input layer are connected to every single node in your next network, and so on, depending on how many layers you have. Fine. Every of these neurons is a function, produces an output, and the bias determines whether it's being what they call activated or not.
Sorry, what's a bias?
Oh, sorry, you just talked about weights. Sorry, did I go too far already?
Sorry, you didn't explain what a bias is, sorry.
I thought you explained weights.
Yes, but a bias is, well, it can be boiled down to a weight, yes. It's just not the term.
Well, it's
not more complicated, but we'll leave it at that.
We didn't really talk about any numbers, but so say your okay. So basically, let's start. Go back in 1 second. So your neurons, what numbers do they work on? Numbers, right? They have
they work on input values. Yes, in the simplest form, that would be numbers, as in floating point numbers. Yes,
and ideally, you want these to be between 0 and 1, right? To give
that depends on the network and on this, and on the arithmetic use and all the rest of it.
Yeah, fair enough. But okay, this is your basic principle of these networks. So that kind of comes back to
using ordinary von Neumann architectures. Quantum neural networks are of course different.
However,
slightly confusing, Martin, but that's okay.
Going back to the von Neumann, sounds very German. Don't mention the Germans.
Whatever you say, Martin. Whatever you say.
Where were we? Yeah. So anyway, okay. Now, okay. Before it's whether we start with an example or whether we go down the internal structure first. Anyway, so imagine you have a neuron that executes a function, a number comes out, right? Fine. You may decide that that number is, or the function may produce 24, and you may say, oh, this 24 is actually way too, I don't want this to activate unless it's over 30 or something like that. So that's your bias, really, which is kind of switching on and off neurons in your network. But again, so carry on. So that's weights and biases. Where were we?
You were explaining your backpropagation network.
No, I was explaining weights and biases and connectedness between layers.
Before I rudely interrupted you.
Okay, so anyway, so you assign a weights to each neuron, right? Is that where we were?
Yes, go ahead.
Or, well, not you,
Continue.
But...
the algorithm.
Yes. There are no people involved here. People, if you're listening, you're not involved. Right. So we got a weight for each neuron. Gives you if you add all those together, you get a weighted sum, right?
Mm-hmm.
And that's really where you can calculate your. It's better with an example, really, isn't it? Think of an example. Because otherwise we're just talking maths, really.
Can't think of one, actually. As much as
Well, what would you solve with a neural network?
Lotto numbers?
Okay. Okay, so what training data would you have for this? Maybe let's go back for one sec. So the idea about the training is to say these are positive examples of a good outcome, right? So you would have lottery numbers and win, yes, no, and then so your in this case your final layer is a yes, no decision, right? Whether a number is a winning number or
yes, you could do that
example.
actually.
Yeah.
Or what you could also do basically is you would take I think the lottery number example is not too far fetched, because essentially if you take the history of all the lottery.
Yeah. Sorry, are you still there? Hello.
If you just do it long enough.
Hello. Sorry.
Yes.
There was a small IT interruption there.
To account you. Sorry. Yes. IT, if you're listening. Get cracking or you will be fine in the morning, my Martin.
In the morning, tonight. Yes. Anyway, carry on.
Okay.
Right. Can you do that again? Because I don't know if it was whose end that was.
No, I mean the lotto number example is actually not too far fetched, because essentially if you do this long enough, you will be able to spot, for a set of lotto numbers being drawn in a certain environment, you will be able to spot certain patterns.
Okay.
In terms of how the balls roll and how the balls fall into particular columns, which of course then represent the lotto numbers being drawn. And as I said, if you do this often enough, you will be able to spot, to isolate patterns, and that's exactly how you would predict the next set of lotto numbers, given the current environment with all the physical parameters into account.
Okay,
if that makes sense.
So, why don't you talk us through that example in a neural network?
Fair enough. So essentially, what you do is, for the first couple of million iterations, you feed data into the network.
And how would you do that?
You would take the environmental parameters, I suppose, plus the balls themselves.
It's on a more sort of data approach. You have a one run of a network would be a single set of numbers. Is that what we're saying? And an outcome?
Plus probably more, because you want to also take into account the time of the day, because that would probably make tiny deviations in gravity. You would also take air pressure into account, because that would affect the way the balls will fall. You want to take the alcohol consumption of the moderator into play, operating the machine. You see, it's getting complex. But if you take all these parameters into account, essentially the way you do is for the first couple of millions of iterations, you just let the balls roll. They will come up with a random pattern, which of course is wrong because it won't reflect.
And sorry to interrupt. The pattern that we're talking about. The pattern that you're talking about here, what does that mean in terms of a neural network?
And say again. Sorry, you were cutting out.
Oh, right. Okay. Yeah, something going on with IT today. Where were we? Yes, sorry. So my question is, what would that pattern look like in a neural network? What does that mean in neural network terms?
You would start with a random distribution of the weights or the biases of the functions.
Mm-hmm.
But then based on the stuff that you feed into the network and that what comes out of the network plus the historical data that you have at your disposal, you can then go back and modify the bias and the weights in the individual neuron self-reflecting sorry, what was the word I'm looking for? In the individual neurons, or individual basically entities representing the neurons, essentially. And this is where the term backpropagation comes from. So you do a run, you get a set of output values. That output that set of output values deviates from the original one, and then you go back modifying the individual structure of the bias, of the function, of the neuron, and so forth. So eventually arriving at the optimal configuration of each and every neuron, which is then and then the network is then able to predict for a specific time, for a specific alcohol consumption of the operator operating the machine. And all the rest of these parameters would be then able to predict the outcome of the next lot to draw.
Yeah. So the does the term cost function mean anything to you?
Go ahead, Martin.
Well, I mean, because you were talking about the output values. So imagine in your example, so with every neural network, you have to define, as I mentioned, your input and output layers, right? So your input layer in your Lotto example would be all the numbers from, I don't know how many numbers are in Lotto, 0 to 9, isn't it? Or does it go up to higher? No, it's higher than that, isn't it?
I don't play Lotto.
50 something or whatever. Anyway, all the numbers from 0 to 55, let's say, for example, those are your your input values.
I think in Germany it's 49 or something, but I may be wrong. Ask the cartel, because some level of funding actually comes from Lotto.
Does it? Oh.
The details will be in the show notes or not.
Excellent. So in your Lotto example, your output would be okay. So then you decide whether you have a yes/no as an input as well, saying that this is a winning combination, right? Or
in the very trivial example, yes.
Yeah, or you would have a yes/no on the output end, saying whatever numbers you feed in, it comes in with a yes/no answer. So those are your kind of.
Or you would attach the sequence to the actual ball drawn.
Yeah,
it depends on how you model it.
Exactly. So it kind of touches on a couple of things. One is availability of data, and then second one, how to structure all this stuff to get what you want of it. Because it's if air pressure is an important factor and gravity is as well, then and you don't have these things, then you kind of have it less likely to have a good outcome.
Absolutely. So the point that Martin is making here, and that's a very valid point, for the more trickier neural networks, basically the function can be quite complex, or the functions in the neuron simulator, let's put it this way, can be quite complex. And in the easiest or in the simplest terms, that would be just a weighted sum, as Martin just explained. But I reckon you won't get away for the slot example with that sort of simple function in the neuron.
Yeah. So anyway, going back to the cost function scenario, your final layer, you're going to assign a cost function on the difference of a good outcome and a bad outcome, right? So if you have, I don't know, in its simplest form, a yes/no, couple of neurons on the end, and the output when you're training it, because it's a self-learning network, as you already mentioned, and the connections need to be established and the weights and biases need to be determined. Your cost function at the end says really if this is a how good was this run, right? So and then
yes,
you can start adjusting them based on that. So the cost function is just really a difference between, again, function based of the difference between a good outcome and what the actual outcome is from the network at that point in time. So which is why you have to keep training it. But yeah, carry on. Why don't you do that?
Yeah. So exactly. So in the simplest way, I reckon the cost function is essentially kill this network by injecting some lethal poison going back to the network, so that all the neurons will die. But I'm exaggerating, of course.
Is this called alcohol, perhaps?
If you're talking human brain, that's probably a very valid approximation.
I have a fun fact for you. It's drinking alcohol actually makes you cleverer.
I knew there was a reason.
Do you know why?
I can think of a multitude of reasons, Martin.
Oh, go on.
Why don't you enlighten me then?
No, go on. Why don't you think of it? I can't.
Well, there's something called, of course, loosening the sensor, and that's exactly what alcohol does.
Okay. No. It actually kills off brain cells as well, right? But
well, it depends on the amount, no?
No.
Well, I mean, if it kills off the right ones.
Exactly. This is the point. It kills off the right ones. Only the poorly performing ones die first. So it's actually a good thing to do.
So, of course, there's a fine line between consuming alcohol and drinking yourself to death.
Yes, and not to mention the liver doesn't really agree with this. But
yeah. Charles Bukowski, if you're listening, we would really love to have you on the show. Medium.com or not?
Yes, indeed.
Okay. Where were we? Backpropagation networks. Yes, of course. We are trying to oversimplify things here. Needless to say, this whole thing is way more complicated than we were able to fit in a episode of Linux Inlaws. There will, of course, be pointers in the show notes. The bottom line is that the backpropagation networks were one of the earliest examples of something called ANNs, artificial neural networks, with the idea of having a model in place that would allow you to dynamically adapt based on the training phase, the functions, the weights, and all the rest of these parameters, and then during in inference phase, you would then put that training to use in terms of let the backpropagation networks predict things, spot patterns, and all the rest of it. And that hasn't really changed over the last couple of decades.
Mm-hmm. Indeed. So how do things like, linear regression and decision trees come into this?
I think I've talked enough for one episode, Martin. You do that. Why do I have to do all the explaining here? Come on, you're the expert.
If I ask a question, you have to answer. So this is how it works. It's kind of the basis of it.
Martin has a hard time acknowledging that I know everything, right from operating systems right up to advanced backpropagation networks. But Martin, hey, now it's your turn. Go ahead.
Yeah, so I mean, it's there is different ways to get to a prediction, right? Which is not a neural network way. So it's really an algorithm that's which is why we were talking about earlier about the difference between machine learning and deep learning. Anyway, so having dealt with that, who came up with this idea about deep learning, or actually not who came up with the idea, but who made this more usable, popular in the recent years?
Google.
Okay, and how and what did they do?
They came up with a very important framework, which will be part of the next part of this 20-part miniseries on artificial intelligence called TensorFlow.
And any other companies that did a lot in this area?
I'm dead sure. Mark Zuckerberg, if you're listening, the email address is sponsor@feedback. Sorry, sponsor@linuxinlaws.eu. Martin, you used to work for Facebook. Why don't you give us an insight?
When did I used to work for Facebook exactly? Have I missed something?
Take a look at your LinkedIn page. I'm dead sure it's on there.
You've hacked this, have you? I thought you were an ethical hacker.
What is hacking, Martin? No, I don't hack other people's LinkedIn profiles.
Oh, glad to hear it. Yeah, so Facebook obviously being the other company that did a lot in this area.
They come up with Torch, right? As in PyTorch.
Indeed, the other popular
Which is, of course, another popular framework. Implementing backpropagation networks, because this is all what they do. They just implement BNPs.
BNPs? BPN.
BPNs. Sorry, long day. We cut this out anyway.
Not to worry, it's just an abbreviation.
Backpropagation networks, yes.
Yeah, so, okay. I think we've kind of covered the basics enough, unless you wanted to go into the math of it, which we probably don't want to.
No.
So we talked
anything
about...
you will add to this topic from a mathematical perspective, Martin, will directly go into the outtakes. I'm going to get in touch with the post-production people. I'm just going to make sure. Don't worry. So you just work away, you just talk, but it'll be in the outtakes.
What about gradient descent? Do you want to cover that? Or?
No, you will, and it will be part of the outtakes.
Oh, I won't bother then. Notes will be in the show notes. Yeah.
Okay, gradient descent for the people who are still awake. Essentially, it's an advanced model to adjust the individual functions in network in neurons. Let's put it this way. We won't go into the details.
Yeah, I wouldn't call it advanced, but anyway, it's fine. Don't worry about it. Okay. So when you speak to the thing about all this stuff is that when you speak to people who are obviously familiar with this topic, they use all these terms, right? So it's useful to know some of them.
So why don't you go ahead and explain some of them, including overfitting?
Overfitting, yes. Well, that comes back to gradient descent, right?
Go ahead.
Do we really want to do this?
Yes, Martin, because you teased it already.
Okay. Okay. Right, what's gradient descent, right? If you have an outcome, right, and you want to decide whether that outcome, the next outcome is better than the other, because we're okay. So as you mentioned before, we're just training this thing with random stuff, weights and biases until we're happy with the output of the cost function represents our final, yes/no answer or whatever it is that we're trying to get out of the network as a decision. Mm-hmm. So where were we?
You were talking about overfitting and...
Oh, yes, sorry, yeah. Yes. Yeah. So in the training phase, you run all this data through and many times and so on. And you compare the current value of the cost function with the previous value and say, is it bigger? Is it smaller? How much bigger is it? And so on. And so you can work out how, if you're going in the right direction of the training, and appropriately adjust your weights and bias. Well, when we say you, it is obviously the algorithm that's doing it. Adjust the weights and biases, right? So that's really what we're trying to do. And with gradient descent, all we're doing is calculating whether we are going in the right direction of getting a better answer, right? And if so, by how much? So if you imagine a simple two-dimensional graph, to keep it simple, and it's it goes up or down. It may go up or down multiple times, and your objective is to find your minimum of the difference between your current output of your cost function and your desired one.
For the 90% of the listenership, I'm having a hard time to follow. Let me oversimplify things here. People imagine you're on a plane in terms of not an airplane, but rather on a two-dimensional surface that has dents reaching into 3 dimensions. Yes, essentially you're trying to get from point A to point B. The trouble is basically if you're for some reason
wait. Why don't we use mountains?
I was just alluding to a hole and being stuck in a hole, but you can, of course, do the same thing with mountains, yes.
Okay, so imagine you're on a mountain and it's foggy, So you can't see the top or the bottom. Actually, let's go with the bottom. Let's go with the bottom. You're on top of this. You climb this mountain. You're going down the other side, and you don't know where the bottom of the mountain is. Fine, and it's foggy, so you can't see either. So you keep going down because your mountain has a gradient until you get to the bottom. But how do you know it is the bottom?
Because it's foggy. Exactly. Yes.
Yeah. So what do we do if it's foggy?
Yes. We actually take out our cell phone and call a helicopter.
What if you?
I'm just trying to break an example.
Well, if you want to break the example,
actually.
if you wanted to break the example and you have a phone and an altimeter, then you could know how high up you were at.
The point
yes.
Yeah. The point that Martin is making here,
you don't know where the bottom is.
Exactly. Yeah. Sometimes it's hard, and this is basically where the magic comes in. For a function to establish if they're not caught in something like a hole, or if they're not just circling around the mountain trying to find its top, or whether they have actually reached the top or not. And this is where the magic comes in with regards to modeling the functions of the neurons. And this is also basically why overfitting is an important concept here. Martin, why don't you explain what overfitting is? Because it's just one step further.
Yeah, fair enough. So how do we explain this with our mountain example? Let's trying to go somewhere with that.
Imagine you have about 6 or 7 mountains on your plane that you're trying to cross. Overfitting, then I'm oversimplifying things. You are trying to identify all the mountains, but for some reason, and that again boils down to the function again, as in the model of your neuron, you're just stuck around one mountain without being able to see the other ones.
That's a good example. Yep.
This is overfitting. So overfitting essentially means you're training the network in the wrong direction.
Yes, because you
again
can't
oversimplifying. Exactly. Yes.
The whole basis of all this is that you don't know where you're going.
Yes. So, for example, taking a very simple domain-specific framework into account, and probably we should skip ahead and explain what a domain-specific network is. Essentially, a neural network is able, and Martin will explain what a convolution network is in a minute. A neural network essentially is able to extract certain features, put them back together again, and then come to the conclusion that a certain item is a smartphone, a laptop, an animal, a can of Coke, or maybe even a pencil. To stick to something called image recognition as the domain here now. So essentially you take a JPEG, you take a PNG, you put this into the neural network, and the neural network is then able to...
Well, you say that, but you don't actually put the JPEG in, right? So...
Well, you put the representation of a JPEG into the network. Yes, sorry.
Yeah.
You feed the data into the network, and the network is then able to extract.
Well, but this is an important there's a lot of things you can do before you feed your data in, right? If you specifically with images,
the details will be covered in part 3 of the mini-series. This will be covered by Martin, and it will be quite a compact episode, only about 5 hours long.
Oh, not sure we can do that in 5 hours.
Exactly. So let me tease the whole thing, and let me give you an outlook of how this is done. You take the picture, and again, Martin, I'm oversimplifying things now. Stay tuned. It'll all be revealed.
Simple is good. Yeah.
It'll all be revealed in part 3 of the mini-series, and it'll be quite complex. As I said, 5 hours maximum. Anyway, it doesn't matter. Okay, you take the picture. The neural network then basically takes a look at the picture, extracts certain features, and puts them back together again. So at the end of these network run of the inference phase of the neural network then comes to the conclusion we are looking at a pencil, a laptop, a smartphone, a soda can, or even at a cat. Coming back to my original remark, Overfitting would then mean that only a certain species of cat can be recognized, but not the cat, not the type of animal as in cat itself. So you would be looking at name a cat species, like a mini lion, in terms of a cat that resembles a tiny lion.
Okay. Yeah.
And other cats wouldn't be recognized if the neural network would be overfitting.
Okay. Very good.
The details, as I said, in part 3 of the mini-series called The Ins and Outs of Domain-Specific Networks.
Well,
the extended version will be about 10 hours, but the the main version that we're going to probably find for 5
we
hours.
Want to do that, yeah. Okay, so how are we doing with our overview?
I think we're still missing one or two things. Martin will cover them in about an hour. Namely, I mean, we all kind of touched upon convolution networks, but why don't you explain a little bit more detail what a convolution network really is?
We don't really. I mean, this is there are lots of different classes of neural networks. Right? I think we've covered the basics, and
yes.
Without going into the details of each and every one of them, which we don't want to do.
We don't. Okay.
There are not in the overview episode, right?
Martin now will try to perform the following miracle: explain the prominent 5 types of neural networks with 5, yes, with 2 sentences for each type.
Okay.
You heard it here first. It's a world premiere. Martin, go ahead.
Okay, so let's have a think. So convolutional neural networks are used for image recognition mainly. LSTM.
That's one sentence, yes.
LSTM for speech. What else have we got? Have you got any for me?
What about generational adverse networks, GANs?
Yeah, so they're quite a nice idea, really. The idea
That's
being
one sentence.
Okay. Okay. The next sentence is going to be a little bit longer.
That's 2 sentences, but you didn't explain the fucking concept.
No. The concept is you run more than one, and what you do is you basically you have a competition, right? It's a competition between networks, and you say, "Oh, this one is doing much better."
Very important. Yes,
goes in the bin. Yeah. Oh, okay.
And why is that important, Martin?
Well, because you want to do it as fast as possible. So the one that is obviously onto a winner. If we think about our mountain example, then yeah.
Yeah, go ahead. Sorry.
No. You carry on.
The core of a generational adversarial network is essentially a competition between 2 competing neural networks. The idea is to
that's way more than 2 sentences.
Backfeed any optimization that was done in one network to the other, meaning it's like spy versus spy, right? The more these 2 spies fight, the better they get at fighting, and that's the overall idea. So if you have a one network in charge of, what's a good example, falsifying a painting, aimed at forging paintings. It'll start with the very basic forging algorithms in terms of methods, but at the very same time, you have a second network trying to guess if a painting is forged or not. By cross-feeding the outcome of these 2 networks, they improve the other one. And this is the overall idea behind this type of a neural network, and this is the hot shit, I think, at the moment in that particular type of science, right?
Yeah, it's just way more efficient in the training, really, because I think that's its main reason. Right, what else have we got?
We, of course, still have convolution neural networks.
Yeah. Used for image recognition.
Yes, but why are they called convolutional?
Because they have more than one convolutional layer.
What's convolution layer, Martin?
Well, you know about the layers we just talked about earlier.
I do, but probably most of our listeners don't.
I mean, it's basically, as you mentioned, the type of function inside the neuron, right? So, in this case, a convolutional operation.
So the idea behind the CNN, to put this slightly more simple.
Why do you get to do this in more sentences anyway?
Because I'm making the rules, Martin. It's quite simple. Okay. The idea behind the CNN is essentially, of course, you still have a neural network at your disposal, and you have an input layer and you have an output layer, but the layers in between vary in terms of interconnectivity, in terms of a number of neurons in a particular layer, and so forth. So the idea behind the convolution network, and hence the name, is to break down the recognition of patterns into certain steps. So, for example, again, oversimplifying, one layer would extract certain aspects of an image, staying in the image recognition domain now, would extract certain aspects of an image. Then the next layer would...
Someone has a nose or something, yeah.
Well, I was just getting there. The next layer would then essentially try to make sense of this extracted feature, and then the third layer would put them back together again in terms of understanding the combined features. So let's take a look at the stuff that Martin has already hinted at. So if you have a
dog decision,
cat, dog, or even a face, right? A face normally, a human face has a nose, has two ears and two eyes, and also has a mouth. So the first layer would take the image, would take the bitmap, and would try to extract two round shapes.
I thought we weren't doing the detail of image recognition.
I'm just using an example. Sorry. would try to extract two round shapes. Would try to expect something oval. Would try to extract something pointy, and also would try to extract something on the sides, prolonged oval shapes. The next layer would then take a look at these extracted features and verify if this is a nose, if this is a pair of eyes, or something like this. And then the third layer would take a judgment of that outcome of the second layer, if we are really looking at a face or not. And if we are, if that's a human face, but that would probably be a fourth of a fifth layer. So this is how CNN work in general. And as I said, this is again oversimplified.
Ah, will do. Details in the show notes. Right.
So if people are still awake, we should probably tease now the second part of this mini-series.
Oh, yes, which is, what was it?
A domain-specific, a concrete example of a backpropagation network.
Was that the second one? I thought we were talking about, No, the third one would actually be a domain-specific framework on top of that infrastructure that we're going to talk about next. I'm confused. Hang on.
So Martin is still struggling with human intelligence. Never mind artificial one. Sorry. Next episode will be the discussion of a concrete infrastructure for a backpropagation network.
Okay.
Yes.
A framework. Yes.
So more than likely, this would be either Torch or TensorFlow. It depends on whether Martin can get his NVIDIA shit together or not, I think.
Why are we doing coding on a podcast?
No, you were suggesting that.
Is that the next one? I thought that was the third one.
No, that was a joke. No, Martin, that was a joke.
You're well on the way of confusing everybody, aren't you?
Am I succeeding, I wonder?
Well, you usually do by creating rooms with the same name about 5 times. Yes.
No, I mean, Martin, if you take a look at the plan, that marketing came up with before you fired them,
exciting,
a couple of weeks back, I might add.
Who needs marketing?
The marketing plan clearly speaks about one framework, and it does mention TensorFlow or PyTorch.
It does indeed. Yes. Okay.
So that will be the second part of the 20-part miniseries. To hit a
actually, you were going to cover TensorFlow, weren't you?
We will cover one specific framework. Yes.
Or we could do both. We do one each.
It depends on whether we want to confine ourselves to 2 or 3 hours.
Yeah.
No, one will be discussed. No, the idea, people, jokes aside. The idea is, after this rather theoretical episode, the jury is still out on this, to give you a more concrete example of one of two popular frameworks. And like cars, like women or men, if you know one, you know them pretty much all.
Beer.
Beer? No, I wouldn't go that far now.
Okay.
Okay, so with that, basically, we have come to the epoxies, as in the picks of the week.
Oh,
What's your pick of the week, Martin? Apart from politicians.
Why would I pick politicians?
I'm saying apart from politicians.
Well, politicians are obviously an anti-pox, but they're every week.
Fair enough.
I had one, so why don't you go first? I'll remind myself what it was.
My pox of the week is something called Atlantic Elba Störtebeker. It's a Eastern Germany. Yes, it's an Eastern German brewery. Störtebeker, if you're listening, the email address is sponsor@Linux Inlaws.
Okay.
And if you just put enough dough into the kitty, we will mention you more than once. I hope.
Okay. Well, or we could always say things about the quality of their brews.
I just did. In case you missed it, yes.
Well, no, you just mentioned their name. So
Well, I said it's a pick of the week because I like the beer.
Okay.
That was implied, sorry.
You did this without them paying us. What's going on here?
It's a pick of the week, Martin. Don't worry about it.
You're missing a trick here. Yeah.
I did mention the email address in case you missed it. Okay, Martin, what's your pick?
What's my pick? Yes, my pick is... it's a good question. I have a few.
One will do.
Yeah, I'm just trying to choose which one is... because I normally choose movies or books. But I'm going to go with... something called Nerva.
What's this?
Which is a CPU-based cryptocurrency.
Nerva
with an N. Yeah.
Nerva. Okay. Details will be in the show notes, I hope.
Quite like their idea behind this. And yeah, if you're listening, send.
The email address is nerva@linuxinlaws.eu. Will be active tomorrow.
Indeed.
Okay. Your anti-pox.
Oh, anti-pox. Well, I think that's pretty easy, isn't it? It's obviously all the politicians in Europe specifically who are being, like countries like France, one of them, that are all saying very silly things about certain vaccines, which is not very clever.
Are they? Okay.
Indeed.
Right. My anti-pox in that case would, of course, be British politicians.
Is what, sorry?
My anti-pox would, of course, in that case be British politicians. But that's okay. Martin, we do have feedback.
We have feedback?
Yes, we do. Great. Yes, you want to read this?
We love our feedback.
We do, yes.
Yes, I'm happy to read the feedback. So we have a feedback from nobody.
Who's nobody?
Thanks, nobody. Well, as someone without just some arms and some legs, I guess.
Fair enough.
Anyway, he obviously has a head because he has a very good observation here. So he mentions other Mac implementations. In the episode, you weren't quite sure if there were other Macs for Linux besides SE Linux and AppArmor, and indeed there are. There is Smack, which is quite uninteresting, as is just another label-based Mac similar to SE Linux. To me, the interesting one is Tomojo, which started as a path name-based file system similar to AppArmor, but later started differentiating between applications based on their process invocation history. So, this means you can apply different policies on, say, /bin/sh, depending on the chain of execution leading to it. Kernel init, getty, login, shell, vs kernel init, SSHD, SH, etc. While this is also possible in AppArmor, it's quite a lot more manual work and more difficult to reason about. Tomojo has much nicer tools than either of the more well-known Macs. SE Linux has given Mac a bad name, which is very true. I would agree with him on that. As being hard and laborious to manage.
Read it out, Mark. Just read it out.
Very, very good observations, this nobody guy. If instead of SE Linux people would be first introduced to Tomojo, they would probably be much more inclined to implement a Mac. Well, there you go. That's brilliant feedback.
Indeed. Nobody, if you're listening, thank you very much for that feedback. I thought smack was the slang term for heroin, but apparently it's a Mac too.
Yes, it is indeed. So Tomojo is actually, as the name implies, something that was originated in Japan.
So it's Tomojo rather than Tomoyo, okay? My Japanese is crap, so I don't really know.
Japanese people, if you're listening, please correct
Yes,
help.
exactly. The address is, as usual, feedback@linuxinlaws.eu. Yes, and if you throw a Japanese course at us, we might be able to mention you in the sponsor ring notes, whatever. But I'm sure to take a look at Tomojo, because that sounds pretty good.
It does. And so smack isn't it is probably a slang term for something else as well. In this case, it stands for Simplified Mac Kernel.
Interesting. You learn something new. This is what I like about this podcast. We rant all day long.
Well,
but
thanks to
the real cool stuff, comes from our listeners. So keep the feedback coming, listeners. We do appreciate that. People, thank you for listening.
Yes,
and thank you for staying awake.
Feel free to turn up on the show.
Yes, please get in touch with us first. Yes, the email address is feedback@linuxinlaws.eu. And before I forget, of course, Martin, we have to plug HPR once again. Ken, if you're listening, thanks for hosting us again.
I don't know, is he listening? Because we never hear from him.
Well, you're not. You don't have to send feedback. But the fact that we're still on HPR, they haven't kicked us out yet. So,
right.
Ken, again, thank you very much.
Does that mean they're not listening to them?
Well, Ken, get in touch.
Yes.
Jokes aside, HPR, thank you very much for hosting us. You have been doing so for way over a year, and we would like to really express our severest gratitude here. And of course, we will be mentioning you further down the road, and we are glad to be part of this network.
We are, indeed.
And with that, see you next time. This is the Linux Inlaws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
This podcast is licensed under the latest version of the Creative Commons license. Type Attribution Share Alike. Credits for the intro music go to Blue Sea Roosters for their song Solid Market, to Twin Flames for their piece called The Flow, used for the segment intros, and finally to Celestial Ground for their song Sweet Justice, used by the Dark Side. You find these and other ditties licensed under CC at Jamendo, a website dedicated to liberate the music industry from choking copyright legislation and other crap concepts.
You've been listening to Hacker Public Radio at hackerpublicradio.org. We are a community podcast network that releases shows every weekday, Monday through Friday. Today's show, like all our shows, was contributed by an HPR listener like yourself. If you ever thought of recording a podcast, then click on our contribute link to find out how easy it really is. Hacker Public Radio was founded by the Digital Dog Pound and the Infonomicon Computer Club and is part of the binary revolution at binrev.com. If you have comments on today's show, please email the host directly, leave a comment on the website, or record a follow-up episode yourself. Unless otherwise stated, today's show is released under a Creative Commons Attribution Share Alike 3.0 license.